4 light-years away, something just disappeared. Not a signal, not a reading, not a number on a graph. A world, a point of light sitting inside the habitable zone of the nearest star system to Earth, 10,000 times dimmer than the star it orbited, appeared in the James Webb Space Telescope's data. Scientists looked at it, measured it, began building a case around it. And then months later, it was gone. No explanation, no gradual fade, just present and then not. That system is Alpha Centauri. We have known it for thousands of years. We named it, we charted it. We pointed every generation of telescope at it and assumed that because it was close, we understood it. Proximity felt like familiarity. Familiarity felt like knowledge. JWST just showed us how wrong that assumption was. If this is the kind of story that changes how you see the universe, hit subscribe. We are also now on Spotify if you want to take this journey with you. Link is in the description. Now, let's go deeper. Here is the first thing you need to understand about Alpha Centauri. It is not far, not in any meaningful sense of the word. 4.3 light-years sounds like a number that should inspire awe, and it does, but not in the direction you might expect. Because that distance, vast as it feels from a human perspective, is almost nothing on the scale of the galaxy. The Milky Way stretches 100,000 light-years from edge to edge. Alpha Centauri sits at 4.3. It is not a distant object. It is not a deep space target. It is, in the language of cosmic geography, the house next door. Think of it this way. If our solar system were a single room, Alpha Centauri would be across the hallway, close enough to hear, close enough that the light leaving it right now will reach your eye in just over 4 years, while light from the far edge of our own galaxy takes 50,000. That closeness is why this system has always mattered, not just as a point of scientific interest, but as a symbol. If planets exist around nearby stars, and we now know planets are everywhere, then Alpha Centauri should have them. If life can form around sun-like stars, this is where we look first. If any system in the sky should feel familiar, readable, and understood, it is this one. And for a long time, that is exactly what we assumed. We were wrong. Alpha Centauri is not a single star. It is a system, 3 stellar bodies bound together by gravity, moving through space as one structure. At the center are 2 sun-like stars, Alpha Centauri A and Alpha Centauri B. They orbit each other in a slow elliptical dance that takes roughly 80 years to complete one cycle. Alpha Centauri A is slightly larger and brighter than our Sun. Alpha Centauri B is slightly smaller and dimmer. Both are close enough to familiar that if either one existed alone, with a rocky planet at the right distance, we would already be searching that planet for signs of life. Further out, loosely tethered to the pair by gravity, is Proxima Centauri, a red dwarf. Faint enough that it cannot be seen with the naked eye, despite being technically the closest individual star to Earth at 4.24 light-years. Proxima is a dim ember compared to its 2 companions, but it matters, because it is Proxima that hosts the most discussed nearby exoplanet, Proxima b, a world sitting in the habitable zone, discovered in 2016, studied obsessively since. Together, these 3 stars form the nearest stellar neighborhood to our own solar system. And that proximity created an expectation that has driven decades of scientific effort. The logic was simple. Distance is the enemy of observation. The farther something is, the harder it becomes to study. The fewer photons arrive, the more noise drowns the signal, the less precision our instruments can achieve. Alpha Centauri removes that problem. It is close enough that our telescopes should be able to extract real detail from it. Planets, atmospheres, structure, the kind of data that remains out of reach for systems 10, 50, 100 light-years away. Alpha Centauri should be the clearest picture we have of any star system beyond our own. That was the assumption. It did not hold. In 2012, a team of astronomers using the HARPS spectrograph one of the most precise planet-hunting instruments of its generation, announced a discovery. A planet around Alpha Centauri, the signal was clean. The paper was published in Nature. For a brief moment, humanity had its first confirmed planet in the nearest star system. 18 months later, the detection fell apart. A reanalysis of the same data showed that the signal was almost certainly an artifact, a pattern generated by the analysis method itself, not by a real planet. The planet did not exist, and what that episode left behind was not just disappointment. It was a warning. Alpha Centauri's data had fooled careful scientists using solid methodology. The system had produced a convincing illusion, which meant every future signal would need to be treated with a level of skepticism that most targets never require. That skepticism became the defining feature of Alpha Centauri research. Over the following years, more signals appeared, hints of structure in the light, subtle variations suggesting an orbiting body. Each one arrived with the same shape, promising, plausible, worth taking seriously. Each one was handled with the caution the 2012 episode had made mandatory. And each one, under further examination, refused to fully hold. Not disproven, not confirmed, something in between signals that weakened when pressed, shifted under different conditions, behaved like evidence that could not commit to being evidence. The system was not empty, but it was also not giving anything away. By the time JWST was operational, Alpha Centauri had developed a reputation unlike almost any other target in astronomy. Not unknown, we knew its distance, its structure, its stellar components with extraordinary precision, but fundamentally unresolved on the question that mattered most. The question of what, if anything, was orbiting there. JWST changed the terms of that question. Not by answering it, by making it stranger. When JWST turned its mid-infrared instrument toward Alpha Centauri, an instrument capable of detecting heat signatures and faint structures invisible to previous telescopes, something appeared in the data almost immediately. A point of light, deep within the system, sitting in a location consistent with the habitable zone of one of its stars. 10,000 times dimmer than the star itself. The team did what scientists always do with unexpected detections. They checked for errors. They looked for instrumental artifacts. They examined whether the brightness of Alpha Centauri's stars, intense enough to create significant interference even for JWST, might be producing a false reading. They ran the analysis multiple times, under different calibration settings, looking for the point where the signal would dissolve into noise. It did not dissolve. For months, the point of light persisted. Faint, stable, sitting exactly where a planet in the right orbit might be expected to produce a thermal signature. Not proof, but not nothing. And then it was gone. Between one observation window and the next, the signal disappeared. No gradual fade, no shift in position, no behavior consistent with an object moving along a predictable orbital path, just absent where it had previously been present. That is not how planets behave. Planets do not vanish. They move along orbits that follow predictable mathematics. They dim and brighten as they transit their stars. They produce signatures that, while sometimes difficult to detect, follow patterns our models can account for. What JWST observed did not follow those patterns, which leaves a set of possibilities, none of them simple. An instrumental effect produced by the extreme brightness of the stars, possible but not fully explained by current calibration models. A transient astrophysical event, something bright and brief occurring naturally within the system. A planet in an unusual orbit, one that moved it out of the instrument's line of sight faster than expected. Or something the data is not yet giving us the framework to interpret correctly. This is where Alpha Centauri stands right now. Not solved, not abandoned. Observed more carefully than ever before, by the most capable instrument humanity has ever pointed at the sky, and more mysterious for it. The disappearing signal has not been explained. The system that was supposed to be our clearest window into the universe next door has instead become the sharpest reminder of something astronomers have always known, but rarely have to confront this directly. Closeness is not the same as understanding. And sometimes, the more carefully you look at something, the less certain you become of what you are seeing. Here is what makes the JWST signal so difficult to dismiss. It is not the signal itself. Faint detections appear in telescope data all the time. Instruments are not perfect. Stars produce interference. Background sources create noise. Unexpected readings are a routine part of astronomical observation, and routine unexpected readings have routine explanations. What makes this one different is the location. The faint point of light that JWST detected did not appear randomly in the data. It appeared inside the habitable zone, the specific region of space around a star where temperatures allow liquid water to exist on the surface of a rocky planet. Not too hot, not too cold. The zone that every planet-hunting mission is designed to prioritize. A random noise artifact does not know where the habitable zone is. A random noise artifact does not appear there, persist for months, and then vanish cleanly. Something produced that signal. The question, the one that has no clean answer yet, is what? To understand why this is so difficult, you need to understand what JWST was actually built to solve. Before JWST, the primary limitation in studying nearby star systems was not distance. Alpha Centauri is close enough that distance was never the issue. The problem was contrast. Alpha Centauri A and B are brilliant stars. The kind of overwhelming brightness that floods telescope sensors the way a flashlight blinds you in a dark room. Any planet orbiting one of them would be millions, potentially billions of times dimmer than the star itself. Trying to detect it with a visible light telescope was like trying to spot a firefly hovering next to a stadium floodlight from a kilometer away. JWST was designed to solve exactly this problem. By operating in the mid-infrared spectrum, it does not look for reflected starlight, the thing that makes planet detection so difficult against a bright star. Instead, it looks for heat, the planet's own thermal emission, its infrared glow, a signature that belongs to the planet itself, not the star. In theory, this shifts the contrast problem dramatically. A planet that is billions of times dimmer in visible light might only be 10,000 times dimmer in infrared, still faint, still difficult, but within the range of what JWST can technically detect around a nearby system. So when JWST looked at Alpha Centauri and found a point of light 10,000 times dimmer than the star, sitting in the right location, this was not a coincidence. This was exactly the kind of detection the telescope was engineered to make. Which is why its disappearance is so hard to explain. Scientists considered 3 categories of explanation. The first was instrumental error. The brightness of Alpha Centauri stars creates a real problem even for JWST. Scattered light, detector saturation, internal reflections, all of these can produce artifacts that look structured rather than random. This was the first thing the team investigated. They reprocessed the data using different calibration models. They compared the signal across multiple observation windows. They looked for the specific signatures that known instrumental artifacts tend to produce. The signal survived the first round of cuts. Not confirmed, but not eliminated. The second category was a transient astrophysical event. The universe produces brief, bright phenomena constantly: stellar flares, dust clumps reflecting light at specific angles, material ejected from a star and briefly illuminated before dispersing. Any of these could produce a point of light that appears for months and then fades. This explanation is scientifically conservative. It does not require a planet. It requires only that something temporarily bright existed in that part of the system. The problem is the location, again. A stellar flare originates from the star's surface. A transient dust structure would follow the dynamics of the stellar wind and move predictably. But the JWST signal appeared within the habitable zone and remained positionally stable during its period of visibility. It did not drift. It did not expand. It sat in place, as a gravitationally bound object in a stable orbit would be expected to do. And then it left. Not faded, left. Disappeared between observation windows in a way that is difficult to reconcile with most transient phenomena, which tend to fade gradually as the energetic event driving them dissipates. Which brings the third category: a planet in an unusual orbit. Not a standard circular orbit. Those would produce a detection that moves slowly and predictably around the star. But an elliptical orbit, one that carries the planet close to JWST's line of sight for part of its cycle, and then pulls it away or behind the star for another, could produce exactly this pattern. Visible for months, then gone. Detectable at certain orbital phases, invisible at others. This is the explanation that remains technically open. It is also the one that generates the most complicated follow-up questions. Because if there is a planet in an unusual orbit around one of the Alpha Centauri stars, that raises questions the data is not yet equipped to answer. How unusual is the orbit, and what caused it to become that way? A planet-forming disk around a binary star system like Alpha Centauri A and B produces gravitational dynamics that can push forming planets into non-standard trajectories. Computer simulations of planet formation in binary systems have repeatedly shown that stable orbits around one star in a close binary pair are possible, but the range of stable orbital configurations is narrower than it would be around a single star like our Sun. A planet in a highly elliptical orbit around Alpha Centauri A or B would spend parts of its year far outside the habitable zone, baking, then freezing, then potentially passing through it again. The question of whether such a world could maintain conditions compatible with liquid water, let alone life, becomes deeply complicated. But that question is secondary. The primary question is simpler. Is it there? The honest answer right now is that nobody knows. JWST is not finished with Alpha Centauri. Additional observation windows have been allocated. Data continues to be gathered. The team working on this detection has not published a final interpretation because there is not one yet. This is science in real time, the messy, uncertain, genuinely unresolved version that rarely makes it into textbooks. What is known is this. Something appeared in the data of the nearest star system to Earth. It appeared in a location that matters. It behaved in ways that resist the simplest explanations. And it disappeared in a way that has not been fully accounted for by any current model. That is not a discovery. But it is not nothing. And in the language of astronomy, where confirmed discoveries take years of follow-up verification, what JWST has produced at Alpha Centauri is something rarer than a clean detection. It has produced a genuinely open question, which means the next round of observations carries more weight than almost anything JWST has done at a comparable target. If the signal returns in the same location with similar characteristics at a time consistent with a predicted orbital period, that changes everything. Not confirmation, but the first credible step toward it. The point where a candidate becomes a candidate worth committing resources to. If it does not return, that changes things in a different direction. Not closure, but a narrowing. A gradual elimination of the planetary hypothesis in favor of something transient, something instrumental, something that currently has no agreed-upon name. Either outcome tells us something important. Either there is a world in the habitable zone of the nearest sun-like star system to Earth, a world that has been hiding from every telescope until now, or something equally strange is happening in that system that produces signals our current models cannot cleanly account for. Both of those possibilities matter. Both of them deserve the next observation. But before we get to what happens next, there is something about Alpha Centauri itself, something about the physics of the system, that makes all of this even harder to explain. Because the disappearing signal is not the first time this system has behaved in a way that defied straightforward interpretation. It is the latest chapter in a pattern that goes back further than JWST, further than any space telescope. And understanding that pattern requires going back to the moment when we first thought we had found something real here, and watching it fall apart in a way that changed how every astronomer who followed approached this system. That moment happened in 2012. And what it revealed was not just a failed detection. It was a warning about the nature of certainty itself. In October 2012, a paper was published in the journal Nature. It announced the discovery of a planet around Alpha Centauri b. The team behind it was not a group of enthusiastic amateurs. They were professional astronomers using HARPS, the High-Accuracy Radial Velocity Planet Searcher, one of the most precise planet hunting instruments on Earth at the time. The kind of instrument that does not make obvious mistakes. The kind of team that does not publish in Nature without checking their work. The planet they reported was small, roughly the mass of Earth. It orbited its star in a tight, fast path, completing one full orbit in just over 3 days. That proximity made it far too hot for liquid water, far too close to its star for anything we would recognize as habitability. But that was beside the point. The point was that it was there. A rocky planet in the nearest star system to Earth, detected with real data by a credible team using a proven method. For a brief moment, it felt like a historic discovery. It was not. The method HARPS used is called radial velocity detection, and it is one of the most reliable tools in planet hunting. Here is how it works. A planet orbiting a star does not just circle passively, it pulls. Its gravity tugs on the star with every orbit, causing the star to wobble slightly around their shared center of mass. That wobble is tiny, almost impossibly small from our perspective, but it produces a measurable effect. As the star moves toward us, the light it emits shifts very slightly toward blue. As it moves away, it shifts toward red. By measuring this shift with extreme precision, astronomers can infer the existence of something orbital causing the motion. HARPS was built to detect shifts in starlight smaller than 1 meter per second, the width of a human hand, applied to a star 4 light-years away. It is an extraordinary piece of engineering, and it had confirmed real planets around other stars many times before. So when HARPS found a radial velocity signal around Alpha Centauri b, a consistent, periodic wobble repeating every 3.5 days, the team took it seriously. They spent years gathering data before publishing. 4 years of observations, over 100 individual measurements. The signal held across all of them. It held until someone looked more carefully at the method itself. In 2015, a separate research team re-examined the same dataset. Not to find a new planet, to test an assumption baked into the original analysis. The HARPS data from Alpha Centauri B contained a problem that the original team had accounted for, or believed they had. Alpha Centauri is a binary system. Alpha Centauri A and B orbit each other. That orbital motion creates its own radial velocity signal, layered on top of everything else the instrument detects. To isolate a planetary signal, the analysis has to mathematically remove the binary's contribution first. The 2015 team found that the method used to remove this contribution had introduced a subtle artifact, not through carelessness, not through negligence, but because the correction itself, the mathematical process of subtracting one signal to find another, had created a periodic pattern in the residual data. A periodic pattern at exactly the frequency of the supposed planet. The planet had not been found in the noise. The planet had been created by the analysis. That sentence requires a moment. A rigorous team using a precise instrument, following standard methodology, published in one of the world's most prestigious scientific journals, and the planet they found was a mathematical shadow. An artifact produced not by Alpha Centauri, but by the act of looking at Alpha Centauri in a particular way. The 2012 episode did not end Alpha Centauri research, it changed it. Every team that followed brought a different level of caution to this system. Signals that might have been treated as promising candidates around other stars were held to a higher standard here. Methods that were considered reliable elsewhere required additional verification before anyone would commit to them at Alpha Centauri. Because Alpha Centauri had demonstrated something that very few star systems ever make this explicit. It can produce convincing illusions. Not through any unusual property of the stars themselves, not through alien interference or cosmic anomaly, simply through the ordinary complexity of a binary system interacting with the ordinary limitations of our analytical methods. The data is real, the instruments are real, but the combination of a complicated source and an imperfect framework for interpreting it creates conditions where the analysis can generate its own signal, one that looks indistinguishable from discovery. That is a deeply uncomfortable realization. Because it means the question is not just whether Alpha Centauri has planets. The question is whether we can trust what we see when we look for them. Several attempts followed the 2012 collapse. In 2021, a team using the Hubble Space Telescope reported a candidate transiting signal around Alpha Centauri, a slight dimming of the star's light, consistent with something passing in front of it. The team was careful. They did not call it a planet. They called it a candidate, something worth following up. Follow-up came. The signal did not repeat. One transit confirmed, a second transit absent. Either the orbital period was too long to catch a second event in the observation window possible, or the first event was not a planet at all. Without a repeating pattern, no claim could be made. In 2021, a separate ground-based effort using a different technique reported hints of a potential planet around Proxima Centauri, already known to host Proxima b, but potentially hosting a second world. This signal, designated Proxima d if confirmed, appeared in radial velocity data at low statistical significance. It remains unconfirmed. Not disproven, not confirmed, held in the same state of ambiguity that has come to define this system. Each of these episodes followed the same basic shape: a detection, a period of careful analysis, a failure to fully confirm, not catastrophic collapses like 2012, but quiet, frustrating, inconclusive endings that left the central question exactly where it started. Are there planets here? And if so, why can't we see them clearly? Which brings the 2012 episode into direct conversation with what JWST found. Because here is the uncomfortable parallel. JWST's signal, the faint point of light inside the habitable zone that appeared, persisted for months and then vanished, is not going to be dismissed the way the 2012 detection was. The method is different. JWST is not using radial velocity. It is using direct imaging in the infrared. The artifact that fooled HARPS cannot fool JWST in the same way. But Alpha Centauri has now demonstrated, more than once, that it does not need to use the same trick twice. The 2012 episode used the binary orbital correction to hide a false signal inside a real analysis. The JWST episode involves a signal that behaves unlike random noise, but also unlike a stable planet. Something that is structured enough to survive initial scrutiny, but inconsistent enough to resist confirmation. Different mechanism, same outcome. A result that cannot be fully dismissed and cannot be fully trusted. And what that pattern suggests across 2012, across the subsequent failed detections, across the JWST data, is that Alpha Centauri does not simply hide its planets. It actively misleads. Not intentionally, not through any physical property designed to confuse, but through the specific combination of two bright stars, complex gravitational dynamics, and the extraordinary technical difficulty of separating faint planetary signals from an overwhelming stellar environment. This system consistently produces the conditions in which our best tools find things that are not quite there, or fail to confirm things that might be. And that raises a question that the 2012 team could not have anticipated. If Alpha Centauri's environment is capable of generating false signals, sophisticated enough to pass initial review by expert teams using proven methods, then what is the standard of evidence required before anything found here can be believed? More data is the obvious answer. More observations, more instruments, more independent verification. The scientific process is designed precisely for situations like this. It is slow and it is frustrating, but it is the only framework that eventually separates real signals from convincing noise. The problem is time. JWST's observation windows for Alpha Centauri are limited. The telescope has many targets. Its time is carefully rationed. Each additional look at this system comes at the cost of looking at something else. And every month that passes without a confirmed detection is also a month during which the JWST signal, whatever it was, sits unexplained in the data. Not resolved, not dismissed, just waiting, which is exactly the state this system has maintained, in one form or another, for over a decade. And the reason that state has persisted, the physical reason, rooted in the architecture of the system itself, has nothing to do with our instruments. It has to do with the fact that Alpha Centauri is not one star. It is two. And that changes everything about what a planet here could look like, and whether it could survive at all. Most stars in the galaxy are not alone. That fact surprises people. The night sky feels like a collection of individual points, each star separate, isolated, burning alone in its own patch of darkness. But roughly half of all sun-like stars in the Milky Way exist in binary or multiple systems. Two stars, sometimes three or four, bound together by gravity, orbiting a shared center of mass across timescales that dwarf human civilization. We live around a single star, so we think of that as normal. It is not the only normal. And the difference between a single star system and a binary system, when it comes to planets, is not a minor technical detail. It is the difference between a calm harbor and open ocean. To understand why, you need to understand what planet formation actually requires. Planets do not appear fully formed. They grow slowly over millions of years from a disk of gas and dust that surrounds a young star. This disk, called a protoplanetary disk, rotates around the star. Material within it collides, clumps together, gradually accumulates mass. Small particles become pebbles. Pebbles become rocks. Rocks become planetesimals. Planetesimals over enormous timescales become planets. The process requires stability. The disk needs to persist long enough for material to accumulate. Orbits need to remain consistent enough for growing bodies to keep collecting mass rather than being flung apart. Around a single star, this process is relatively straightforward. Gravity from the central star dominates. The disk rotates predictably. Planets form. Around a binary system, the situation changes fundamentally. Because now there are two gravitational sources, two stars, each pulling on the disk from different directions as they orbit each other. And that creates regions of the disk where the combined gravitational influence of both stars tears material apart faster than it can accumulate. Those regions are called orbital instability zones. And around Alpha Centauri A and B, which orbit each other at distances ranging from roughly 11 to 36 astronomical units, depending on where they are in their 80-year orbital cycle, those instability zones are not small. Here is the specific problem. Alpha Centauri A and B are what astronomers call a close binary. Close not in everyday terms. Their minimum separation is still about the distance from our Sun to Saturn, but close in the context of stellar dynamics. That proximity means their mutual gravitational influence extends across a significant portion of the space around each star. Simulations of planet formation in this kind of system consistently produce the same result. Planets can form around each individual star, but only within a limited range of distances. Too close to the star, and the orbit is stable, but the planet forms quickly and tends towards small, rocky configurations. Too far from the star, and the gravitational influence of the companion begins to disrupt orbits, elongating them, tilting them, eventually destabilizing them entirely. The boundary of that stable zone around Alpha Centauri A sits at roughly 3 to 4 astronomical units from the star. Beyond that, a companion star's gravity makes stable orbits increasingly unlikely over long timescales. 3 to 4 astronomical units. For reference, Earth orbits our Sun at exactly 1 astronomical unit. Mars orbits at 1.5. The habitable zone around Alpha Centauri A, the region where temperatures allow liquid water, sits at roughly 1 to 2 astronomical units from the star. Which means the habitable zone falls inside the stable orbital region. A planet could, in principle, exist there. The simulations say so. Multiple independent models of planet formation in Alpha Centauri's binary configuration have produced stable rocky planet analogues in the habitable zone of Alpha Centauri, the gravitational environment, while more complex than our own solar system, does not automatically prevent planet formation in that region. This is the hope. Now here is the crush. Knowing that a planet could exist in the habitable zone and detecting one there are two entirely different problems. And the binary configuration that merely complicates formation actively destroys detection. Remember how radial velocity works. The instrument measures tiny shifts in a star's light caused by the gravitational tug of an orbiting planet. The shift is small meters per second, sometimes less. Around a single star in a quiet system, that signal can be isolated and measured with sufficient precision. Around Alpha Centauri, there is a second star producing its own radial velocity signal, a massive one. Alpha Centauri A and B pull on each other constantly. That pull creates a radial velocity signature orders of magnitude larger than any planet could produce. Before a planetary signal can be found, the binary's contribution has to be removed from the data. And we have already seen, in 2012, what happens when that removal process goes slightly wrong. But radial velocity is only part of the problem. Direct imaging, the technique JWST uses, faces a different version of the same obstacle. Both stars are bright, extremely bright in infrared wavelengths. Their light floods JWST's sensors when the telescope points at this system, creating what astronomers call a glare problem. Any faint signal, a planet, a debris disk, a thermal emission from something small and warm, has to be separated from the overwhelming brightness of two stellar sources simultaneously. Not one flashlight in a dark room. Two, pointed directly at the camera. The team that analyzed JWST's Alpha Centauri data spent significant effort developing custom processing techniques, specifically to handle this glare. They subtracted the stellar contribution using models calibrated to the specific brightness profile of each star. They looked for residual signals that remained after the subtraction. The faint point of light in the habitable zone was one of those residuals, which raises an immediate question. If the HARPS signal in 2012 was created by an imperfect subtraction process, a mathematical artifact left behind when binary motion was removed from radial velocity data, then what confidence exists that JWST's signal is not a similar artifact left behind when stellar brightness is removed from infrared imaging data? Different instrument, different method, same fundamental challenge. Subtract something large and complex from a dataset, and whatever remains carries the uncertainty of that subtraction. The scientists working on this data are aware of this problem. They are not naive to the parallel. The 2012 episode is part of the institutional memory of Alpha Centauri research. Nobody who works on this system forgets it. But awareness of a problem does not solve it. The honest position, which the research team has maintained publicly, is that the JWST signal cannot currently be attributed to a specific source with confidence. It survived initial artifact checks. It does not match the known signatures of the most common instrumental errors. But it also does not behave with the consistency that would be required to call it a confirmed detection. It sits in a space that this system has created before. Plausible, unconfirmed, resistant to simple explanation. There is one additional layer to the binary problem that matters here. Even if a planet exists in the habitable zone of Alpha Centauri A, even if JWST's signal is real, and there is a rocky world sitting at the right distance from the right star, the conditions on that world would be profoundly shaped by the presence of a second sun. Alpha Centauri B, at its closest approach, would appear in the sky of such a planet as a brilliantly bright star. Not as bright as Alpha Centauri A, not close to it, but bright enough to be clearly visible as a disk, not a point. Bright enough to cast shadows at night. The planet would experience a sky unlike anything in our solar system, a primary star overhead, and a second stellar body tracking across the sky, its apparent size changing over the course of decades as the two stars move through their 80-year orbit. The effect on climate would be real. During periods when Alpha Centauri B is closer in its orbit, the additional radiation reaching the planet would increase. Not dramatically, the geometry means B's contribution is modest compared to A's, but measurably. Over the timescales relevant to habitability, these variations would create a climate that oscillates in ways our own planet does not experience. Whether life could arise in that environment is a question nobody can answer yet. Whether the planet exists is a question nobody can answer yet either. Both answers depend on the same thing: more data, better data. Data that the next generation of instruments may finally be capable of producing, if the problem of separating signal from noise in a binary system can be solved in ways that have eluded every previous approach. Because what the binary problem ultimately reveals is this: Alpha Centauri is not just a difficult target because of what we do not know about it. It is a difficult target because of what we do know. We know the orbital dynamics well enough to model where planets could exist. We know the stellar brightness well enough to understand why detecting them is so hard. We know the detection history well enough to see the pattern of failed confirmations. We have more knowledge about this system than almost any other beyond our own. And that knowledge has produced not certainty, but a precise understanding of exactly why certainty is so difficult to reach. That is a strange place to stand. Knowing enough to see the problem clearly, not knowing enough to solve it. And somewhere inside that gap, between what the models say is possible and what the data refuses to confirm, there may be a world. Or there may not be. Either way, the nearest star system to Earth is not finished surprising us. And the next surprise was already waiting, not around Alpha Centauri A or B, but around the third member of this system. The one that most astronomers had written off as too hostile, too violent, too unstable to be worth serious attention. Until a planet was found there anyway. Proxima Centauri is not a welcoming star. It is small, roughly 1/8 the mass of our Sun. It burns cool and dim, radiating only a fraction of the light and heat that our own star produces. If you stood on a planet orbiting Proxima and looked up at it, you would not see a brilliant yellow disk dominating the sky. You would see something smaller, redder, and quieter. A star that looks almost tired compared to the one we know. That dimness has consequences. For a planet to sit in Proxima's habitable zone, the region where liquid water could exist on its surface, it would need to orbit extremely close to the star. Not close in the way Earth orbits our Sun, dramatically closer. The habitable zone around Proxima Centauri sits at roughly 5% of the distance between Earth and our Sun. A planet in that zone would complete one full orbit in approximately 11 days. 11 days per year. Orbiting at a distance that, in our own solar system, would place it deep inside the orbit of Mercury. That proximity creates a problem that goes beyond temperature. It creates a trap. When a planet orbits close enough to its star, gravity does something irreversible to it. It locks it. The technical term is tidal locking. The same process that keeps our moon always showing the same face to Earth, because Earth's gravity has, over billions of years, slowed the moon's rotation until its orbital period and rotational period became identical, operates on close-orbiting planets with far greater force. A planet in Proxima's habitable zone, at that distance, would almost certainly be tidally locked to its star. One side permanently facing Proxima, bathed in continuous red light, heated constantly with no night to cool it. The other side permanently facing away, in endless darkness, frozen. Between them, a narrow band, the Terminator line, the permanent boundary between eternal day and eternal night, where temperatures might fall into a range compatible with liquid water. A thin strip of world that is neither roasting nor frozen. A permanent twilight zone circling the planet like a ring. That is the most optimistic version of habitability for a tidally locked world. And even that version assumes the atmosphere survives long enough to matter. In 2016, a team of astronomers announced the discovery of a planet around Proxima Centauri. Designated Proxima b, it was found using the radial velocity method, the same technique that had produced the false positive around Alpha Centauri b 4 years earlier. But this time, the signal was cleaner. The star is quieter than Alpha Centauri b in certain measurable ways, and the orbital period, 11.2 days, was short enough that multiple cycles could be confirmed across the observation window. The discovery stood up. Proxima b is real. It orbits in the habitable zone of the nearest individual star to Earth. Its minimum mass is roughly similar to Earth's, possibly larger, depending on the angle of its orbit relative to our line of sight, but not dramatically so. It is, by every technical definition, a potentially habitable world. And then the follow-up studies began. The first problem was the star itself. Proxima Centauri is what astronomers call a flare star. Red dwarfs of its type are magnetically active in ways that sun-like stars are not, or at least, not to the same degree. They produce stellar flares, sudden, violent releases of energy from the star's surface. Bursts of ultraviolet radiation and X-rays that erupt with little warning, and can be orders of magnitude more intense than anything our sun typically produces. Our sun flares, occasionally, modestly. The Earth's magnetic field and atmosphere absorb the energy without significant damage to surface conditions. Proxima flares constantly. A 2016 study examining Proxima's flare activity found that the star produces flares roughly every few hours. Not minor fluctuations, events powerful enough to briefly increase the star's ultraviolet output by factors of hundreds. In March 2016, a single flare from Proxima increased its brightness by a factor of over 68 within 2 minutes. For a planet at Proxima b's distance, that kind of flare is not a weather event. It is a bombardment. The ultraviolet radiation from a single major flare could strip away atmosphere at rates that, over geological timescales, would leave a planet essentially bare. No ozone layer, no protection for any surface chemistry that might be trying to become biology, just a rocky world being systematically scoured by its own star. Hope meet crush. But the story does not end there. Because science rarely lets a question close cleanly. Several researchers pointed out that tidal locking, combined with the right atmospheric composition, might actually provide some protection. A thick enough atmosphere could redistribute heat from the day side to the night side, preventing the extreme temperature gradient that makes tidally locked worlds seem uninhabitable. Circulation models suggested that certain atmospheric configurations could produce a stable, temperate region covering more than just the Terminator strip. And regarding the flares, some researchers proposed that life, if it ever arose on Proxima b, might have done so in environments that are naturally shielded from surface radiation. Deep oceans, underground, in the kind of extreme environments where life on Earth has repeatedly demonstrated it does not need easy conditions to survive. These arguments are not fantasy. They are serious scientific proposals, published in peer-reviewed journals, made by researchers who understand the hostility of the environment and are asking whether that hostility is truly absolute. The answer so far is, we do not know. What we know is that the conditions on Proxima b would be nothing like Earth. The radiation environment is more intense. The light arriving at its surface is predominantly infrared and red, a spectrum that photosynthesis, as we know it, would struggle to use efficiently. The gravitational dynamics of tidal locking reshape every aspect of atmospheric and geological behavior. But nothing we know rules out the possibility that something could survive there. And that is a statement that deserves to sit for a moment. the nearest planet to Earth that sits in the habitable zone of its star, the closest potentially habitable world we have ever found, is a place that bombards its surface with radiation every few hours, keeps one face in permanent frozen darkness, and receives light so red that our version of photosynthesis would not recognize it as useful. And we cannot rule out that something lives there. Then in 2020, the story added another layer. A second signal appeared in Proxima's radial velocity data, smaller than Proxima B's signal, consistent with a planet roughly a quarter of Earth's mass, if confirmed, one of the smallest exoplanets ever detected, orbiting in a much tighter path at only about 4% of the distance Proxima B orbits. This candidate was designated Proxima Day. It was not in the habitable zone, far too close for liquid water at its distance, but its existence, if confirmed, would mean Proxima hosts at least 2 planets, which transforms it from a single planet system into something that begins to look like a planetary system, with all the structural implications that carries. A year later, a third candidate signal appeared, this one farther out, possibly in a 5-year orbit, too uncertain to publish as a detection, but present enough in the data to be noted and flagged for further observation. Proxima Centauri, the star most astronomers had written off as too violent and too dim to host anything interesting, may host a family of worlds. None of them confirmed beyond the first. All of them real possibilities. All of them sitting 4.2 light-years from Earth, slightly closer, even, than the 2 sun-like stars most people think of when they hear Alpha Centauri. And this is where Proxima B connects directly back to the JWST signal. Because Proxima B was found with radial velocity, JWST cannot easily observe Proxima B directly. The geometry of its orbit makes transits unlikely from our viewing angle, and its proximity to such a dim star creates its own set of detection challenges. But JWST can observe Alpha Centauri A and B. And what it found there, a faint infrared point of light inside a habitable zone around a sun-like star that appeared for months and then vanished, sits in a different category from Proxima B. Not a radial velocity signal, not a pattern in stellar wobble. A direct detection of something that was physically present in the system, emitting heat, and then was not. If Proxima B taught us that the nearest stars can host real worlds, even under hostile conditions, then the JWST signal asks a harder question. What if the nearest sun-like star, the one with a stable habitable zone, the one that does not flare constantly, the one whose conditions are closest to our own sun, what if that star is hiding something too? Not a signal inferred from stellar wobble. Something that was actually there. Something that JWST looked at directly. And something that, despite months of observation and careful analysis, still has no agreed-upon explanation. That is where the investigation stands. And the next step in understanding it requires going deeper into what JWST actually saw, not just that there was a signal, but what the signal looked like in detail, what it did and did not match, and why the scientists analyzing it have not been able to close the question in either direction. Because the data itself tells a story. And that story is stranger than a simple disappearing planet. The signal had a temperature. That detail matters more than almost anything else in this story, because a random noise artifact does not have a temperature. A reflection from a detector surface does not have a temperature. Instrumental ghosts, the false readings that telescopes produce when overwhelmed by bright sources, tend to be cold in the infrared, structureless, spectrally flat. What JWST detected inside the Alpha Centauri system had thermal structure. It was warm, Not star warm, not the thousands of degrees that a stellar surface produces, but warm in the way that a rocky planet sitting at the right distance from a star would be warm, absorbing radiation, re-emitting it as heat, producing an infrared signature consistent with a surface temperature that falls, roughly, within the range where liquid water does not automatically boil or freeze. That is not proof of anything, but it is the specific kind of signal that was never supposed to be easy to explain away. To understand what JWST actually did when it observed Alpha Centauri, you need to understand the instrument it used. JWST carries 4 scientific instruments. The one most relevant to this observation is called MIRI, the mid-infrared instrument. It operates at wavelengths between 5 and 28 micrometers. For context, visible light, the light your eye detects, sits at wavelengths between roughly 0.4 and 0.7 micrometers. MIRI sees light that is 10 to 60 times longer in wavelength than what human eyes can process. At those wavelengths, the universe looks different. Stars are still bright, very bright, but their dominance over nearby objects decreases compared to visible light. A rocky planet at the right temperature begins to glow with its own thermal emission, rather than simply reflecting its star's light. The contrast between star and planet, while still enormous, becomes more manageable. MIRI was designed with exactly this application in mind, detecting the thermal emission of planets around nearby stars, finding worlds not by the light they reflect, but by the heat they produce. When MIRI pointed at Alpha Centauri, it was doing precisely what it was engineered to do. And it found something. The detection process involved multiple observation windows spread across several months. In each window, JWST collected raw data from the Alpha Centauri system. That raw data is not a clean image. It is a field of photons, many of them scattered and distorted by the overwhelming brightness of Alpha Centauri A and B. The stars saturate portions of MIRI's detector, producing blooming effects, diffraction spikes, and scattered light halos that extend across a significant portion of the field of view. The analysis team had to subtract all of that. They used a technique called point spread function subtraction. A point spread function, PSF, is the characteristic pattern that a star produces on a detector. Every telescope has one. It depends on the optics, the wavelength, and the detector geometry. By modeling the PSF of Alpha Centauri A and B with high precision and subtracting it from the raw data, the team could isolate what remained signals that could not be attributed to the stars themselves. In most systems, this process produces a clean residual, faint background galaxies, detector artifacts, occasionally a companion star or brown dwarf, almost always nothing unexpected. In Alpha Centauri's residual, there was something at a position consistent with the habitable zone of Alpha Centauri A. A point source, compact, located approximately 1 astronomical unit from the star, within the region where a rocky planet in a roughly Earth-like orbit would be expected to sit. And it was warm. The team tested that warmth against every alternative explanation they could construct. The first was scattered light from the star itself. Alpha Centauri A is bright enough that even after PSF subtraction, residual scattered light can create structures in the data. The team examined whether the signal's position, brightness, and spectral characteristics matched the expected profile of a scattering artifact. They did not match cleanly. Scattering artifacts from a stellar PSF tend to follow predictable patterns, arcs, rings, radial streaks extending outward from the star. The detected signal was compact and point-like. It did not follow the geometry expected from scattered light. The second alternative was a background source. a distant galaxy or quasar that happened to be positioned behind the Alpha Centauri system from JWST's viewing angle. Background sources are common in astronomical data. They are usually identifiable because they remain fixed against the background sky, while nearby stars move slightly over time due to proper motion. Alpha Centauri moves. It is close enough and fast enough that its motion across the sky is measurable over months. If the detected signal were a background object, it should have appeared to shift relative to Alpha Centauri as the star moved. The time checked for this shift. The signal moved with the star. Whatever produced it was gravitationally associated with the Alpha Centauri system, not a background object, something physically present in the system, orbiting, or at minimum co-moving with one of its stars. That eliminated the second alternative. The third alternative, and the one that has not been eliminated, is an astrophysical transient, something temporarily bright within the system that was not present before the observation window and was not present after. This is the category that the signal's disappearance most naturally suggests. A transient could be many things: a stellar flare from one of the stars, illuminating a cloud of dust or gas at just the right angle to produce a point-like reflection. A cometary body, something large and icy, passing close enough to Alpha Centauri A to heat up and briefly glow before dissipating. A collision between two rocky bodies in the system, generating a short-lived cloud of debris with a distinctive thermal signature. Each of these has been discussed by researchers examining the data. Each of them has a problem. Stellar flare reflections tend to produce signals that vary rapidly, brightening and dimming on timescales of minutes to hours, following the flare's own energy curve. The JWST signal persisted across multiple observation windows separated by weeks. That persistence is inconsistent with most flare reflection scenarios. Cometary heating produces a characteristic spectral signature, emission features from sublimating volatile compounds. The team looked for those features in the signal's spectrum. They were not clearly present. A collision event would produce a cloud of debris that expands and cools over time, a signal that should fade gradually and change shape as the material disperses. The signal, during its period of visibility, did not show the expected spatial expansion. None of the transient explanations fit cleanly. And neither does the planetary hypothesis, because planets do not vanish between observation windows without an explanation for where they went. What the team was left with is a signal that passed the initial elimination of the most obvious false positives, ruled out as scattered light, ruled out as a background object, but could not be definitively matched to any known astrophysical source. In the language of the paper that discussed these observations, the signal is described as a candidate of uncertain origin. That phrase carries more weight than it might appear to. Uncertain origin does not mean unknown. It means that the data is consistent with multiple explanations, and no single explanation is dominant enough to claim the result. It means the analysis has been done carefully, and the standard alternative hypotheses have been tested, and the signal survived that testing without being explained. It is the scientific equivalent of saying, "We looked at this carefully, we checked the obvious answers, and we still do not know what it is." That is an uncomfortable place for a result to sit. But it is where this one sits. There is one more detail about the signal that has not been widely reported. During the period of its visibility, the team examined whether the signal's brightness was consistent over time, or whether it varied between observation windows. It varied, not dramatically, not in a way that would immediately suggest a flare, or a transient. But the signal was measurably brighter in some windows than others, a low-level variability that added another layer to the interpretation problem. A stable planet in a circular orbit should produce a relatively consistent thermal signature over short timescales. It would brighten and dim predictably as it moved through different phases of its orbit, but those variations would follow a pattern tied to its orbital period. The variations in the JWST signal did not clearly follow an orbital pattern. They were irregular, which means either the signal is not a planet, or it is a planet with surface or atmospheric conditions that produce irregular thermal emission, something that has no obvious analog in the planetary science literature. Or the variations are measurement noise in a faint detection, and the true signal is more stable than the data suggests. All three remain open. And this is the point in the investigation where the data runs out. Not because the team stopped looking, but because what remains requires something the current dataset cannot provide. A confirmed orbital period. A second disappearance and reappearance that follows a predictable timeline. A spectral signature that matches a known source type rather than sitting ambiguously between categories. Those are the things that would close this question in one direction or another. And the only way to get them is to keep watching. But watching Alpha Centauri with JWST has its own complications that go beyond the signal itself and extend into the physical environment of the system. An environment that contains something no one expected to find at this level of density. Something that may be hiding worlds, or creating the illusion of them. In 2015, a telescope called VLTI, the Very Large Telescope Interferometer in Chile, pointed at Alpha Centauri and found something nobody had specifically gone looking for. Dust, not a faint trace, not an ambiguous reading that required careful interpretation to identify. A confirmed detection of warm dust sitting close to Alpha Centauri A, in the inner region of the system, near the star, in the zone where planets would orbit. The finding was published, it was noted, and then for the most part it was set aside. Because dust around a star is not unusual. Most stellar systems contain some level of dust, material left over from planet formation, continuously replenished by collisions between asteroids and comets, slowly dispersing over billions of years. A dust detection in isolation does not imply anything specific about planets. It is simply a feature of a planetary system in the process of evolving. What makes Alpha Centauri's dust different is not that it exists. It is where it exists, and how much of it there is. The specific type of dust detected around Alpha Centauri A is called exazodiacal dust. The name comes from analogy with our own solar system's zodiacal dust, the faint band of material visible in very dark skies just after sunset or before sunrise, produced by debris from comets and asteroid collisions within the inner solar system. Our own zodiacal dust is relatively sparse. It is bright enough to see under good conditions, but thin enough that it does not meaningfully interfere with observations of the planets within it. Alpha Centauri's exazodiacal dust is not sparse. The VLTI measurements suggested that the dust around Alpha Centauri A is somewhere between 100 and 1,000 times denser than the zodiacal dust in our own solar system, sitting in the inner system. In the habitable zone region, 100 to 1,000 times denser. That number changes everything about how this system can be observed. Imagine trying to photograph a candle flame sitting inside a fog bank. The flame is real, the light it produces is real, but the fog scatters and diffuses that light in every direction, creating a glow that fills the space around the flame and makes it nearly impossible to see the flame itself clearly. The denser the fog, the more the flame's light blends into the surrounding diffuse glow. Now imagine the fog is also warm. It is emitting its own infrared radiation, its own heat signature, filling the detection field with a thermal background that any instrument trying to detect the faint warmth of a small, distant object has to somehow separate from the fog's own emission. That is what exazodiacal dust does to planet detection. A rocky planet in the habitable zone of Alpha Centauri A would sit inside a cloud of warm dust that is itself producing infrared emission. The planet's thermal signature, the thing JWST is specifically designed to detect, would be buried in the dust's own glow. Separating the two requires knowing, with extraordinary precision, exactly what the dust contribution looks like at every position in the field. That is not currently possible. The dust distribution is not uniform. It clumps, it varies with distance from the star. It is influenced by the gravitational dynamics of the binary system, which can create asymmetries and structures within the disk. Without a detailed, high-resolution map of exactly where the dust is and how bright it is at each position, any point source detected within it carries an irreducible uncertainty. The possibility that what appears to be a compact object is actually a local concentration of dust that happens to be brighter than its surroundings. A local concentration of dust, or a planet. The data cannot always tell the difference. And now the JWST signal acquires a new layer of ambiguity. Because the faint point of light detected in Alpha Centauri's habitable zone, the signal that appeared warm survived initial artifact checks, moved with the star, and then disappeared, was sitting inside this dust field. Every alternative explanation the team tested assumed, to varying degrees, that they were looking at a clean environment, a point source against a well-characterized background. But the background was not clean. The background contained dust, warm, infrared-emitting dust in the exact wavelength range MIRI uses, dust that is dense enough to produce its own structures in the data, dust whose distribution is complex enough that even a detailed PSF subtraction may not fully account for it. Which means there is a fourth alternative explanation for the JWST signal that is distinct from the three discussed in the previous section. Not instrumental artifact, not background galaxy, not astrophysical transient. Dust clump, a localized concentration of exazodiacal material that was temporarily brighter than its surroundings, perhaps stirred by the gravitational dynamics of the binary system, perhaps the result of a recent collision between planetesimals in the inner disk, that appeared as a point-like source in MIRI's data and then dispersed or moved out of the field as the system evolved. This explanation is consistent with every characteristic of the observed signal. The warmth, the compact appearance, the movement with the star, the eventual disappearance. All of it fits a transient dust concentration as well as it fits a planet. And that is the problem. But the dust does something else beyond complicating detection. It raises a question about the system's history that has direct implications for habitability. Exazodiacal dust at the density measured around Alpha Centauri A does not simply exist passively. It is constantly being replenished. Dust particles are small. They experience radiation pressure from the star, which gradually pushes them outward. They experience Poynting-Robertson drag, which causes them to spiral slowly inward and eventually fall into the star. Without a continuous source of new material, the dust cloud would dissipate on timescales of thousands to millions of years, short, in the context of a stellar system billions of years old. The fact that dense dust exists now means something is producing it. The most likely source is an active population of colliding bodies in the inner system. Asteroids, comets, planetesimals that have not yet settled into stable, non-crossing orbits. Objects that are still encountering each other with enough frequency and force to grind themselves into the fine particles that form the dust cloud. In our own solar system, the period of heavy bombardment, when the inner solar system was dense with colliding planetesimals, ended roughly 4 billion years ago. The current zodiacal dust is a remnant of a much calmer era. The collisions that produce it are infrequent. The system has, in the relevant sense, settled. Alpha Centauri's inner system may not have settled. A dense, active dust population suggests ongoing dynamical activity in the region where planets would orbit. And ongoing dynamical activity, collisions, gravitational perturbations, unsettled orbital configurations, is precisely the kind of environment in which a forming or recently formed planet would face continuous disruption. Not necessarily destruction. Planets in our own solar system survived the bombardment period and went on to develop conditions compatible with life. But the bombardment period on Earth was rough. And what it produced in terms of surface conditions was nothing a complex organism would have recognized as hospitable. There is a scenario that ties all of this together. Not a confirmed scenario, not one any researcher has published as a definitive interpretation, but one that is consistent with everything the data currently shows. Alpha Centauri hosts a young, dynamically active inner system. Planetesimals are still colliding. Dust is being produced at high rates. In the midst of this activity, a planet may have formed, or may be in the process of forming, at a distance consistent with the habitable zone. That planet's orbit is not yet stable in the long-term sense. It is subject to perturbations from the active debris population and from the gravitational influence of Alpha Centauri, be its thermal signature, buried in the dust cloud, is difficult to isolate from the background. When JWST observed it, the planet was present. Its emission contributed to a localized brightening in the habitable zone region. When JWST observed again, the geometry had shifted. The planet had moved in its orbit. A concentration of dust had closed behind it, filling the gap its brightness had created. The net result in the data was indistinguishable from the signal having vanished. This scenario requires a planet. It requires active dust dynamics. It requires a specific geometric alignment that allowed the detection in the first observation window and prevented it in the next. It is possible. It is not confirmed. And the dust that would test this hypothesis, the dust that would either reveal the planet's orbital motion within it or demonstrate that the signal was entirely a dust artifact, cannot be mapped at the resolution required by any instrument currently in operation. The telescope that could do it does not exist yet. It has a name, it has a design, it has a funding proposal. And if it is built, it would not be the only new tool approaching this problem from a completely different direction, one that does not try to observe Alpha Centauri from a distance of 4 light-years at all, but instead proposes to send something there directly. Something small, something fast, something that would arrive within a human lifetime. And what it might find when it gets there depends entirely on whether the signal JWST detected was real. In April 2016, a press conference was held in New York City. Standing at the podium were Stephen Hawking, the physicist whose name needs no introduction, and Yuri Milner, a Russian-Israeli billionaire who had already committed hundreds of millions of dollars to the search for extraterrestrial intelligence. Beside them were representatives from some of the most respected institutions in astrophysics. They announced a project called Breakthrough Starshot. The goal was simple to state and almost incomprehensible to execute. Send a spacecraft to Alpha Centauri within a generation. Not a generation ship, not a crewed mission, not the kind of vessel that would carry human beings across 4 light-years of void, something far smaller. A fleet of probes, each one roughly the size and weight of a postage stamp, attached to sails made of material thinner than a human cell. Those sails would be accelerated by an array of ground-based lasers powerful enough to push each craft to roughly 20% the speed of light. 20% the speed of light. At that velocity, the journey to Alpha Centauri would take approximately 20 years. Not generations, not millennia, 20 years. In the context of everything this series has established about the impossibility of reaching another star system, the crushing distances, the energy requirements, the biological barriers, 20 years sounds almost casual. It is not casual. But it might be possible. The physics behind Starshot are real. They do not require new discoveries or theoretical breakthroughs that have not yet been made. Laser propulsion is understood. Light sails have been demonstrated. The Planetary Society's LightSail 2 mission proved the concept in Earth orbit in 2019. The engineering challenges are enormous, but they are engineering challenges. Problems of fabrication, materials, and scale, not problems of physics. The laser array required to accelerate a sail to 20% light speed would need to deliver roughly 100 gigawatts of power in a focused beam for approximately 10 minutes. That is more power than most countries currently generate. Focusing it precisely enough to remain on target as the sail accelerates is an optical challenge that has no current solution at the required scale. The sail itself must be reflective enough to absorb the laser's momentum without being destroyed by it. At 100 gigawatts of incident power, a sail that is even slightly absorptive would vaporize in seconds. The material requirements push into territory that does not yet exist in any laboratory. And then there is the interstellar medium. At 20% the speed of light, even the thin scattering of hydrogen atoms between stars becomes a hazard. Each atom from the sail's reference frame arrives with the energy of a particle accelerator beam. Over 4 light-years of travel, the cumulative radiation damage to the sail's electronics, if it carries any, would be severe. These are real problems. Breakthrough Starshot's response to them is not to pretend they are solved. It is to fund the research that might solve them and to be honest about the timeline. The project's founders have consistently said that a launch is decades away, perhaps 2060, perhaps later. The press conference in 2016 was not an announcement of a ready mission. It was an announcement of intent and a commitment of initial funding, $100 million to begin answering the engineering questions. But the intent is serious. And the destination is Alpha Centauri. Assume for a moment that the engineering problems are solved. A fleet of Starshot probes launches. They accelerate to 20% the speed of light. They travel for 20 years in the dark between stars, bombarded by cosmic rays, running on power systems that must survive 2 decades of operation without any possibility of repair. They arrive at Alpha Centauri. They have approximately 1 hour. That is the transit time through the system at 20% light speed, the window during which each probe passes close enough to its target to gather data. There is no slowing down. At this velocity, there is no propulsion system capable of decelerating the craft into orbit. The probes fly through the system at a fraction of light speed and keep going. 1 hour. In that hour, each probe must photograph whatever it can, measure whatever it can, and begin transmitting data back to Earth. That transmission, traveling at the speed of light, will take 4 years to arrive. So the full timeline, if everything works, looks like this: 20 years of travel, 1 hour of observation, 4 years for the data to return. 25 years from launch to first results. If it works, now place the JWST signal inside this scenario. The probes are being designed before anyone knows whether there is a planet in Alpha Centauri's habitable zone. The mission's scientific objectives were defined around the known planets, Proxima b primarily, and whatever might be discovered around Alpha Centauri A and B before launch. But if the JWST signal is real, if there is a world sitting in the habitable zone of Alpha Centauri A, then the Starshot probes would fly directly through the region where that world orbits. 1 hour of observation. Cameras capable of resolving features at the scale of continents, if the orbital geometry is favorable and the probe passes close enough. Instruments capable of detecting atmospheric composition from the thermal emission of a planet it passes within a few million kilometers of. In that single hour, a Starshot probe could potentially gather more information about a habitable zone planet around Alpha Centauri A than JWST could accumulate in years of observation from Earth. Not because the probe is more powerful than JWST, but because proximity changes everything in observation, exactly as it changes everything in astronomy generally. 4 light-years away, a planet is a faint point of thermal emission buried in stellar glare and exazodiacal dust. 4 million kilometers away, it is a world. But there is a version of this scenario that is less exciting and more disturbing. The Starshot probes arrive, they transit the system. Their cameras scan the habitable zone of Alpha Centauri A during the 1-hour window. And they find nothing there. No planet, no world. No object at the position where JWST detected its signal. What would that mean? It could mean the JWST signal was not a planet, a dust clump, an artifact, a transient that has long since dissipated by the time the probes arrive decades later. That would be disappointing but not surprising, given everything the history of Alpha Centauri observation has demonstrated about false positives. Or it could mean something stranger. A planet in an elliptical orbit might not be in the habitable zone when the probes arrive. It might be at a different orbital phase, closer to the star, or farther from it, or behind it entirely. The 1-hour transit window does not allow for a comprehensive survey of all orbital positions. A planet that was present when JWST looked might be exactly where it always was when Starshot arrives, simply not in the probe's direct line of sight during the transit. An absence in the Starshot data would not be proof of absence in the system. This is the fundamental challenge of a flyby mission to a place you cannot slow down in. 1 hour, 1 geometry, 1 moment in the orbital dance of a system that has been evolving for billions of years. There is a detail about the Starshot mission that rarely gets mentioned in the coverage of it. The probes would not only be looking for planets, they would be looking for signs of something else. The scientific instruments being discussed for Starshot include not only cameras and spectrometers, but magnetometers and particle detectors, instruments capable of detecting the signatures of a planetary magnetosphere, the kind of magnetic field that Earth possesses, and that plays a significant role in protecting a planet's atmosphere from stellar wind erosion. A planet with a magnetosphere, even detected indirectly through its effects on the local particle environment during a high-speed flyby, would be a world with a dramatically higher probability of retaining an atmosphere. An atmosphere is not life. But no atmosphere is, almost certainly, no life. The detection of a magnetosphere around a planet in the habitable zone of Alpha Centauri A would be among the most significant scientific results in human history. And it is within the measurement capability of the probes being designed right now. Starshot is not a certain mission. It may not launch in the timeline its founders envision. The engineering problems are real, and the funding required to solve them is orders of magnitude larger than what has been committed so far. There are serious people in the scientific community who believe the project's timeline is optimistic by decades. But it represents something that is genuinely new in the history of this story. For the first time, the question of what exists in the Alpha Centauri system is not purely a question of remote observation. It is a question with a potential answer that does not depend entirely on what we can see from here. We might go and look. Not us precisely, not human beings, but something we built, carrying instruments we designed, following a trajectory we calculated, arriving at a system that has resisted understanding for decades, and spending 1 hour gathering the kind of data that no telescope can produce from 4 light-years away. Whether that mission reveals a world or reveals nothing, it will end one chapter of this story definitively. But before the probes could ever launch, before any of the engineering problems could be solved, there is a question that the JWST signal has forced into the open. A question that changes what Starshot is actually looking for. Because if the signal is real, if there is a planet in the habitable zone of the nearest sun-like star to Earth, then what that planet looks like, what lives on its surface, what its sky contains, none of it resembles anything in our solar system. Not because it is alien in some undefined way, but because the physics of existing under two suns, in a system with a history of bombardment, wrapped in a cloud of warm dust, orbiting at a distance that produces a year shorter than our own, produces a world that follows rules our experience has never had to prepare us for. And imagining that world is not speculation. It is the next step in understanding what JWST may have actually found. Assume the signal is real. Assume there is a planet. Set aside for the length of this section every question about detection and confirmation and data interpretation. The scientists can have those questions back when we are done. Right now, take the simplest possible reading of what JWST found, a warm object in the habitable zone of Alpha Centauri A, and follow it to its conclusion. What would that world actually be like? Not in the vague, speculative way that science fiction handles the question, but specifically, physically, based on what we know about the system, about stellar dynamics, about planetary science, about the conditions that exist around a sun-like star 4 light-years from Earth. What would you see if you were standing on it? The answer is stranger than most people expect. Start with the sky. Alpha Centauri A is a G-type star, slightly larger and brighter than our Sun, but close enough in character that its light would look familiar. From the surface of a planet orbiting it at roughly 1 astronomical unit, the star would appear slightly larger than our Sun appears from Earth. The light would be slightly warmer in color, a touch more yellow-white than the pale yellow we see from our own star. So far recognizable. Then you look across the sky to find the second sun. Alpha Centauri B, at its current separation from a varying between 11 and 36 astronomical units across its 80-year orbit, would appear in the sky of this planet as an extraordinarily bright star. Not as large as Alpha Centauri A, not a second disk dominating the sky with equal intensity, but far brighter than anything visible in our own night sky. Depending on where it sits in its orbital cycle, it would be bright enough to cast faint shadows, bright enough that the side of the planet facing it during nighttime hours would never experience true darkness. A night sky with a star so bright it casts shadows. The length of the shadow would shift over decades as Alpha Centauri be moved through its 80-year orbit, closer sometimes, appearing larger and brighter, then receding, dimming, but never disappearing entirely. Every year on this world, the shadow-casting companion would sit at a slightly different position in the sky. Every decade, its brightness would measurably change. The planet's inhabitants, if there were any, would live inside a sky that was not static, but slowly, visibly evolving across timescales longer than human lifetimes. Now consider what that second star does to the climate. The primary energy source is Alpha Centauri, a planet at 1 astronomical unit from A, receives roughly the same solar flux that Earth receives from our Sun, enough to maintain liquid water on the surface under the right atmospheric conditions. Alpha Centauri b adds to that flux. Not dramatically, at typical orbital separations, B's contribution to the planet's total energy budget is a fraction of a percent at minimum, rising to perhaps a few percent when B is at its closest approach. But that variation is not negligible over geological timescales. Every 80 years, the planet experiences a subtle warming as B reaches periapsis, its closest point to A. Then, over the following 40 years, a gradual cooling as B recedes toward apopsis. These cycles would not produce dramatic climate swings. They would not trigger ice ages or mass extinctions on their own. But they would be present, measurable, built into the climate record the way our own Milankovitch cycles, variations in Earth's orbital parameters that occur over tens to hundreds of thousands of years, are built into our ice core data. A geologist on this world, drilling into ancient ice or sediment, would find an 80-year climate signal embedded in the record. A signal that came not from the planet itself, but from the motion of a companion star 60 times farther away than the planet's own sun. Then there is the dust. A planet forming inside the exazodiacal dust cloud that surrounds Alpha Centauri A would not exist in a clean system. It would be embedded in a diffuse haze of fine particles, remnants of ongoing collisions in the inner system, continuously replenished, slowly settling but never fully absent. From the surface, this dust would be nearly invisible during daylight hours. The sky would appear blue, or whatever color the atmospheric scattering produced, depending on the atmosphere's exact composition, much as ours does. But at certain angles, in certain lighting conditions, the dust's presence would reveal itself. The zodiacal light on Earth, the faint pyramid of light visible along the ecliptic before dawn or after dusk, is produced by our own sparse inner solar system dust. It is subtle, barely visible from dark locations, the kind of thing you have to specifically look for to notice. Around Alpha Centauri A, with a dust cloud 100 to 1,000 times denser, the zodiacal light equivalent would not be subtle. It would dominate the twilight sky, a broad, luminous band extending across the horizon at dusk and dawn, visibly bright, structurally complex. Not the soft glow familiar to dark sky observers on Earth, but something more prominent, a feature of the sky that would be obvious, present every clear evening, shaped by the combined gravitational dynamics of a binary system into patterns that no planetary astronomer trained on our solar system would immediately recognize. What about life? The honest answer is that we do not know whether a planet in Alpha Centauri A's habitable zone could support life. We do not know that with certainty about any planet beyond Earth. The conditions we have described, a second sun casting shadows, an 80-year climate cycle, an active dust environment, are unusual by the standards of our solar system. But unusual is not the same as incompatible. Life on Earth has colonized environments that are extreme by any reasonable standard. deep ocean hydrothermal vents where sunlight never penetrates, hypersaline lakes where the water is close to saturated with salt, the interior of nuclear reactors. Bacteria have been found in each of these places, thriving. The specific challenge on a world around Alpha Centauri A would not be any single extreme condition, but the combination of them. An active bombardment environment during the system's early history, similar to, but potentially more intense than, Earth's late heavy bombardment period, followed by ongoing collisional activity in the inner disk. Ultraviolet and X-ray contributions from both stars during flare events. The gravitational perturbation of a companion star that periodically stirs the outer regions of the system and deflects comets and asteroids into the inner zone. These are not gentle conditions. But Earth's conditions were not gentle either during the period when life first arose. The earliest confirmed evidence of life on Earth dates to roughly 3.5 billion years ago. At that time, Earth's surface was being regularly bombarded by large impactors. The atmosphere was oxygen-free. The oceans were geochemically unlike anything alive today. And life appeared anyway. If it happened here under those conditions, the question of whether it could happen under the different, but not obviously more hostile conditions of a planet around Alpha Centauri A does not have a clear negative answer. But there is a detail about this hypothetical world that connects directly back to the JWST signal and its disappearance. A planet in an elliptical orbit, one that swings through the habitable zone, but also carries it significantly closer to Alpha Centauri A at certain orbital phases, would experience dramatic seasonal variation. Not the mild four-season cycle that Earth's axial tilt produces, something more extreme. A year that begins with temperatures compatible with liquid water, passes through a period of intense heat as the planet swings close to the star, and then recovers as it retreats. Under those conditions, life, if it exists, would not look like life on Earth. It would be adapted to cycles of heat and recovery, to a sky that changes in brightness over years rather than hours, to a gravity environment shaped by the constant low-level perturbation of a second gravitational source 90 million kilometers away at closest approach. Whatever biology that planet hosts would be ours only in the most distant, chemical sense. The DNA would be foreign, the metabolic pathways would be foreign. The relationship to light, that fundamental driver of photosynthesis as we know it, would be shaped by a spectrum that, while similar to our sun's, carries a different energy distribution in the wavelengths biology uses most. It would be life, but not life as we have ever seen it. And detecting it from 4 light-years away through a dust cloud, using instruments built for a different kind of planet in a different kind of system, would be harder than anything we have yet attempted. Which raises the question that the JWST signal makes impossible to ignore. If there is a planet in the habitable zone of the nearest sun-like star to Earth, and if that planet hosts some form of life, then that life has been our neighbor for as long as our planet has existed. For 4 billion years, something may have been living 4 light-years away. And we have had no idea. Not because we were not looking, not because we lacked curiosity or intelligence or scientific drive. Because the universe is extraordinarily good at keeping secrets. Even from neighbors. Even when they are right next door. And if that is true, if life can exist this close and remain invisible to everything we have built to find it, then the question of why we have never detected any signal from any intelligent civilization anywhere in the universe takes on a different weight entirely. Because the silence we have been hearing may not mean what we assumed it meant. In 1950, during a casual lunch conversation at Los Alamos National Laboratory, physicist Enrico Fermi asked a question that has haunted astronomy ever since. Where is everybody? His colleagues understood immediately what he meant. The Milky Way contains somewhere between 200 and 400 billion stars. Many of them are older than our Sun. Many of them host planets. If intelligent life is even remotely common, if it arises wherever conditions permit and develops technology at rates comparable to what happened on Earth, then the galaxy should be teeming with civilizations. Some of them should be millions of years more advanced than us. Some of them should have developed interstellar travel. Some of them should be visible. Instead, we see nothing. No radio transmissions that cannot be explained by natural processes. No optical beacons. No megastructures blocking starlight in patterns too regular to be natural. No evidence, anywhere in the electromagnetic spectrum, that intelligent technological civilization exists beyond Earth. The silence is absolute, and it is profoundly strange. This is the Fermi paradox, a tension between what the numbers suggest should be true and what observation actually shows. The numbers say we should not be alone. Observation says we are. For 70 years, scientists have proposed solutions. Some argue that intelligent life is extraordinarily rare. Others argue that civilizations arise frequently but destroy themselves quickly. Others propose that advanced civilizations exist but choose not to communicate, or communicate in ways we have not yet learned to detect. Each solution has problems. Each solution leaves parts of the paradox unresolved. And then JWST looked at Alpha Centauri and found something that appeared, persisted, and vanished without explanation. And the Fermi paradox suddenly became less abstract. Here is why the JWST signal matters. If there is a planet in the habitable zone of Alpha Centauri A, if the signal is real and the world exists, then the nearest potentially habitable planet to Earth sits 4.3 light-years away. 4.3. Not 100 light-years, not 1,000, 4.3. Close enough that a radio signal sent from Earth would arrive in 4 years. Close enough that a response, if anyone were listening and chose to reply, would return in 8. 1 human decade for a question and an answer. That proximity reframes the entire structure of the Fermi paradox. If intelligent life can arise on a planet in the habitable zone of a sun-like star, and if that planet exists at Alpha Centauri, then we are not talking about civilizations separated by distances so vast that contact becomes a theoretical abstraction. We are talking about neighbors. Neighbors close enough to know we are here. Close enough to have been watching. Close enough that, if they wanted to communicate, the conversation would not require generation ships or responses that arrive centuries after the sender has died. They could call. We could answer. The round trip would fit inside a single human lifetime. And yet we have heard nothing. We have looked at this system with every generation of telescope. We have measured its stars with extraordinary precision. We have searched for planets using radial velocity, transit photometry, direct imaging. We have allocated observation time on JWST to stare into this system and extract whatever faint signals exist in its habitable zone. And what we have found is ambiguity. Not absence, not a confirmed empty system, but signal after signal that refuses to resolve into certainty. Detections that appear and then dissolve under scrutiny. A thermal signature that was present for months and then vanished. If there is a world there, it has been extraordinarily difficult to see. If there is life there, it has given no indication of its presence. If there is intelligence there, if something on that world developed technology, looked up at the sky, saw our sun 4 light-years away, and chose to send a signal, we have not detected it. The silence at 4 light-years is the same silence we hear from the rest of the galaxy. That silence has an explanation in the standard models of the Fermi paradox. Life is rare, intelligence is rarer, technological civilization is rarer still. The odds of 2 independent origins of intelligent life occurring within 5 light-years of each other in a galaxy 100,000 light-years across are vanishingly small. We are alone in our local neighborhood, not because life cannot exist at Alpha Centauri, but because the universe is cruel with probabilities. That has been the default position for most of the history of SETI. Look at distant stars, survey the sky, cast the net wide because the thing you are looking for is rare, and proximity does not increase the odds of finding it. But there is a different explanation. One that the JWST signal, if it is real, makes much harder to dismiss. What if life is not rare? What if the conditions that allow biology to arise are common, and planets in habitable zones around stable stars are sufficient to produce it more often than not? What if Alpha Centauri hosts a world where something lives, something that metabolizes, reproduces, evolves across billions of years? And what if that life has been there the entire time we have been looking, and we simply cannot see it? Not because it is hiding, because detection, even at 4 light-years, is harder than we assumed. This is the possibility that the history of Alpha Centauri observation has made uncomfortably plausible. We have looked at this system for decades. We have used the best tools available at each stage of our technological development, and every time, the system has produced results that resist clean interpretation, signals that look like planets until they do not, dust clouds that obscure the regions where planets should be. Binary dynamics that complicate every detection method we apply. The 2012 HARPS detection was not the result of bad science. It was the result of a system complex enough to fool good science. The JWST signal is not the result of instrumental failure. It is the result of an environment where separating a faint planetary signature from stellar glare, exozodiacal dust, and binary gravitational effects pushes our current capabilities to their absolute limit. If we cannot confirm the existence of a planet in the habitable zone of the nearest sun-like star, a star we have studied intensively, at a distance where every photon carries orders of magnitude more information than it would from a star 100 light-years away, then what does that say about our ability to detect life anywhere? What does it say about the silence we have been interpreting as absence? The possibility that needs to be considered, seriously, not as speculation, is that the galaxy is not silent because it is empty. It is silent because we are still learning how to listen. From 4 light-years away, biology does not announce itself. It does not send signals. It does not construct visible structures. What it does is alter the chemistry of its planet's atmosphere in ways that are difficult to explain through geology alone. On Earth, the most obvious biosignature is oxygen. Our atmosphere is 21% oxygen. That concentration is not chemically stable. Oxygen is reactive. Without a continuous biological source, photosynthesis, primarily, Earth's atmospheric oxygen would be consumed by chemical reactions with surface rocks and would disappear over geological timescales. The fact that it persists is evidence of biology. Detecting that signature from 4 light-years away requires spectroscopy. a detailed measurement of the light passing through the planet's atmosphere as it transits its star, light that carries, embedded in its spectrum, the absorption features of whatever molecules are present. Most planets do not transit from our viewing angle. The ones that do produce signals that are extraordinarily faint. JWST can detect them, for some planets, under the right conditions. Alpha Centauri A is extremely bright. If there is a planet in its habitable zone, we do not know whether it transits. Even if it does, even if JWST observes it during transit, even if the atmosphere contains oxygen or methane, the brightness of the star and the density of exozodiacal dust may be enough to drown the signal entirely. Detecting life at Alpha Centauri, even if it is there, may be beyond what current instruments can achieve. We built the most powerful space telescope in history. We pointed it at the nearest star system that could potentially host life. We found something, a faint thermal signature in the habitable zone, exactly the kind of signal that a planet would produce. And we cannot confirm what it is. Not because the data is bad, not because the scientists are careless. Because the system is complex enough, and the signal is faint enough, and the tools we have are just barely capable enough, that the result sits in the space between detection and confirmation. And if that is true at 4 light-years, then the silence from the rest of the galaxy may not mean what we thought it meant. It may not mean there is nothing out there. It may mean that out there is harder to see than we assumed. Radio SETI assumes that advanced civilizations produce radio leakage, accidental transmissions that spill out into space. That assumption was reasonable in the 1960s, when Earth's radio transmissions were growing rapidly. But Earth's radio leakage has not kept growing. As communication technology has improved, we have shifted from high-power broadcast signals to low-power targeted transmissions. Fiber optics carry data that never enters the radio spectrum. Satellite communication uses tightly focused beams. If an alien civilization 100 light-years away were listening to Earth with the same instruments we use to listen for them, they would see a planet whose radio signature has been fading for decades. Not because we stopped being technological, because we got better at it. If that is the typical trajectory, if most civilizations pass through a brief radio-loud phase and then go quiet as their technology matures, then the galaxy could be full of civilizations that are simply no longer shouting. And we would hear silence. Not because no one is there. Because we are listening for the wrong thing. Alpha Centauri has demonstrated repeatedly that detection is not the same as presence. The 2012 planet was not there, but the signal was real enough to pass peer review and get published in Asterisk Nature. The JWST signal may be a planet, or it may be dust, and the data cannot yet tell the difference. If we cannot cleanly detect a planet 4 light-years away, in a system we have studied more intensively than almost any other target in the sky, then what confidence should we have that we could detect a civilization 100 light-years away, if that civilization were not actively broadcasting? The silence we have been hearing may not be the silence of an empty galaxy. It may be the sound of a galaxy full of things we do not yet know how to see. The next JWST observation of Alpha Centauri is already scheduled. It will happen in the coming months. The telescope's controllers have allocated observation time. The coordinates are locked, the instruments are calibrated, and somewhere in the administrative machinery of space science, there is a date circled, a moment when JWST will turn its primary mirror toward that familiar system 4 light-years away and look once more for the signal that vanished. This observation will be different from the ones that came before. It will not be a discovery mission. It will not be searching blindly for something that might be there. it will be a confirmation attempt. A deliberate effort to answer a single, specific question. Does the thermal signature return? That question has two possible answers, and both of them are unsettling. If the signal returns, if JWST detects a faint thermal source in the same region of the habitable zone, at a time consistent with an orbital period, exhibiting the same thermal characteristics it showed during the initial detection, then we will know something is there. Not what it is. Not yet, but that it exists, that it moves in ways that gravity dictates, that it is real enough to be detected twice under different observational conditions by the same instrument. That would be extraordinary. A planet would exhibit exactly this pattern. An object orbiting Alpha Centauri A would return to the same location on a predictable schedule, would maintain the same thermal signature as it did before, would be consistently observable if we point the right instruments at the right place at the right time. But so would other things. A piece of debris from a collision between asteroids might produce a thermal signature that persists across months. Dust clouds can linger in a system for years, and there are exotic possibilities, structures, artifacts, remnants of mega-engineering projects that would produce detectable heat signatures and could, in principle, be in the habitable zone of Alpha Centauri A. If the signal returns, the next step would be to extract more information. Spectroscopy, detailed thermal mapping. An attempt to infer the composition, the size, the orbital mechanics of whatever is producing the signal. Each new observation would add constraints, narrow the possibilities, move the system from ambiguity toward understanding. It would take time, years probably, multiple observation campaigns, coordination with ground-based telescopes, the slow, methodical process of science turning data into knowledge. But it would be possible. The signal would be real, confirmed, replicable, and the investigation would move forward on a solid foundation. The second possibility is worse. If the signal does not return, if JWST observes Alpha Centauri during the predicted return window and finds nothing, no thermal source in the habitable zone, no sign of whatever produced the initial detection, then the paradox deepens. The first signal was not instrumental error. The data quality was good. The detection methods were sound. Something produced that thermal signature. Something left a mark in the infrared spectrum that JWST detected and recorded. But if that something is no longer there, if it has moved or cooled or disappeared entirely, then we are left with a different set of mysteries. Did the object move out of the habitable zone? Planets migrate, asteroids drift. But that would require a specific set of orbital conditions, a specific configuration of gravitational forces. It is possible, but it would be a remarkable coincidence, to detect something during a brief window and then watch it leave. Did it cool? Thermal signatures fade when objects cool. A large asteroid, freshly formed or recently exposed by a collision, would be hot enough to detect. Over weeks and months, it would cool and become invisible to infrared telescopes. But the initial detection persisted across months of JWST observations. The object did not cool appreciably during that time. For it to cool completely between the initial detection window and the follow-up observation window would require the object to be significantly smaller, or colder, or more distant than the original data suggested. Or did it disappear? That is the possibility that carries real weight, because if something was there, real enough to be detected, consistent enough to be observed multiple times across a span of months, and then it was no longer there, then we have to ask, why? Objects do not simply vanish from the universe. They move or cool or break apart or get hidden by dust, but they do not cease to exist. So if the signal is gone, then either our interpretation of the initial detection was wrong, it was not what we thought it was, or something caused it to change in ways that made it undetectable. A deliberate change, a concealment, a shift in behavior. That is not something that planets do. Planets orbit in predictable patterns, they cool gradually, they do not hide. But something that was aware of being detected, something that knew it was being observed by a telescope 4 light-years away, something that chose to change its behavior, or mask its signature, or move away. That would be a different matter entirely. This is the dark possibility that hangs over the next observation. Not that we will find nothing, that would be merely disappointing. But that we will find evidence of something that was there, and then was not. Evidence of a pattern interrupted. Evidence that something aware was watching back. And that is more disturbing than silence. Because silence is absence. It is a simple state, the object is not there, or we cannot detect it, or it does not exist. Silence is something we understand, even if we find it frustrating. But silence after a signal, that is information. That is a message. The next observation will happen regardless of what we expect or fear. JWST does not hesitate, it does not second guess. It simply collects data, and we interpret what it shows us. If the signal returns, the investigation will continue. Deeper observations, attempts to resolve the object, spectroscopy to infer composition. Searches for correlated signals at other wavelengths. The slow, methodical process of turning a mysterious thermal signature into a confirmed exoplanet, or asteroid, or artifact, or whatever it turns out to be. If the signal does not return, a different set of investigations would begin. Searches for similar signals elsewhere in the system. Analysis of the original data to see if we missed something. Re-examination of the system's dust distribution, its binary dynamics, its gravitational environment. An attempt to understand not what disappeared, but why. Either outcome advances the question. Either outcome moves this investigation from the space of ambiguity into the space of data that can be tested, refined, and used to build the next hypothesis. And either outcome will be strange. Because Alpha Centauri, this system we have studied intensively, this nearest stellar neighbor, this place where a potentially habitable planet might or might not exist, has already demonstrated something uncomfortable. It has shown us that even at 4 light-years, even around a sun-like star, even with the most powerful telescope we have ever built, even when we point our instruments directly at a target and use every technique we know, detection remains difficult. Confirmation remains elusive. And the silence, when we listen for neighbors who should be close enough to hear us, remains absolute. The next observation will either break that silence or deepen it. And whichever happens, the answer will haunt us. The truth about Alpha Centauri is that we may never know what that thermal signature means. The next observation may return a signal. It may not. The data may clarify. It may deepen the mystery. And even if we eventually confirm that a planet exists in the habitable zone of Alpha Centauri A, even if we detect biosignatures in its atmosphere, even if we find every piece of evidence that life is there, we still may never know if anyone is listening. That is the crushing reality that 70 years of the Fermi paradox has taught us. The universe is very good at hiding. And we are very good at seeing only what we expect to see. We built JWST because we wanted to find exoplanets. We pointed it at Alpha Centauri because we wanted to confirm the existence of worlds we knew should be there. We found a thermal signature, and we interpreted it through the lens of what we were looking for: a planet, a world, something we could name and catalog and understand through the frameworks we already possess. But what if that framework is too small? What if there is something in the habitable zone of Alpha Centauri, A, that is not a planet, and not dust, and not any of the categories we have built to organize the cosmos? What if it is something we do not yet have a name for? The Fermi paradox has always assumed that the silence of the galaxy means one of two things. Either we are alone, or we are being avoided. Either intelligent life is vanishingly rare, or it exists but does not want to be found. But there is a third possibility. What if intelligence in the galaxy has learned something that we have not yet learned? What if the reason we see no signals, no probes, no evidence of advanced civilizations is not because they are rare or hidden, but because they have discovered that visibility is dangerous? That the universe does not reward the loud. That broadcasting your presence to the cosmos is a good way to attract attention you do not want. That survival for a technological civilization might depend on learning to be invisible. Alpha Centauri could be a case study in this lesson, a world where life arose, where intelligence emerged, where technology developed, and where at some point someone made a choice. To stop broadcasting, to stop announcing their presence, to become quiet and listen and wait. The thermal signature we detected, if it is real, might be the only thing they have ever let us see. An accidental leak, a moment of carelessness, or perhaps intentional, perhaps a test, perhaps a way of asking quietly if anyone out there was paying attention. We were, but we could not confirm what we were seeing. And so the moment passed, and the signal faded, and the silence returned. This is speculation. This is not science. This is the kind of thinking that makes scientists uncomfortable because it lives in the space between data and story, between evidence and interpretation. But it is also the only framework that makes sense of what we have observed. The Fermi paradox is not a paradox at all. It is a filter, a way of asking who gets to survive in a universe where visibility is dangerous. The answer, perhaps, is those who learn to hide. And if that is true, then the silence we hear from the galaxy is not the absence of life. It is the sound of a galaxy full of civilizations that have already learned the most important lesson: how to disappear. The next JWST observation will tell us if Alpha Centauri was listening. But it may never tell us what was on the other end of that signal. And perhaps that is exactly the point.